Okay, I will continue with practical transformer when you have voltage source on both sides of transformer. Suppose that here you have, you have voltage source here and here. So we want to know what's the flux linkage when you have two voltages and two currents. We will start with the flux linkage for coil 1. For coil 1, we can write it's the summation of lambda 11 and lambda 12 that is equals to self-inductance of coil 1 times the current of coil 1 plus the mutual inductance between the coil 1 and coil 2 times the current of coil 2. We can write the same thing for the flux linkage of coil 2. That is summation of two parts. One of them is because of self-inductance itself, L2, and another one is for L12 or L21 is the same. It's the mutual inductance. So if the flux linkage change with the time, we can take derivative and we can calculate the voltage. We can write this equation because the voltage terminal here is the voltage drop here, this part, R1, I1, and this part is because of the winding here. So the voltage, the terminal voltage V1 is equals to R1 times I1 plus derivative of lambda 1 with respect to time. And we can write it because we had this expression. We can write this one, R1 I1 self-inductance of coil 1, derivative of current, of its current, and L12 derivative of the other currents. So we can write the same thing for voltage of this part. V2 is R2 I2 plus derivative of lambda 2. That its resistance is here, and L21 because of the mutual inductance, and L22 because of self-inductance of the transformer. So we calculated V1 and the V2 voltage terminal of both sides. And if we write this equation in the phasor form, or during the steady state condition, you can write phasor form. As you know, we are not in the transient condition. During the steady state condition, we can write a formula in phasor form. And so we can write the voltage and the current based off its phasor. It's the phasor of voltage of the voltage terminal of the primary and the current of the primary section and the current of the secondary winding. So if you remember from the previous slide, we had resistance and the self-inductance and the mutual inductance. And so this part can be called impedance 1,1 and the impedance 1,2, Z12, because of the mutual inductance. And this part is because of the self-inductance and the resistor of the wire. And we can write the same thing for voltage, terminal voltage of secondary winding. So V2 is the phasor form. It's not the sinusoidal function, it's a phasor. It's a complex value. And it's the phasor of currents the current of coil 1 and the current of coil 2. So it's proportional to the mutual inductance, the resistance of wire of the second coil, and the self-inductance of coil. And if we write in the matrix form, we have this expression. It's a vector of voltage, vector of current, and this matrix that shows the different impedance when we have a transformer. Based on this matrix, we can create equivalent circuit. We can have this equivalent circuit for the transformer. Suppose that you have a transformer here, and it is the equivalent that you can use in your analysis. So, but from this side, it's the voltage of the primary winding, and AV2, here is V2. But this V2 is referred to the other side. So we have AV2 because A is N1 over N2. And we know that V1 over V2 is N1 over N2. And this part is A. We can write V1 is V2 A. Do you remember when you move? So if you move V2 from other side to this side, we can use just the ratio between the turns of primary and secondary winding. We have this expression, we have this schematic representation for the equivalent circuit for the transformer. We have resistance here, we have self-inductance, mutual inductance, the ratio we have here, self-inductance of the secondary winding, and the mutual inductance. And again, the resistance. So, but if you want to have the simpler representation, you can use this one. So it's the equivalent of the transformer. You have voltage here and here, and there is resistance for the wires, and it's the reactance. We call it the reactance, series reactance. X1 and X2 are series leakage reactance that are calculated based off these inductance. They are calculated based off self-inductance and mutual inductance. This is the final equivalent for the transformer. And this part is important because it's related to magnetizing, and we call it susceptance. As you remember, we have impedance, that is R plus J X. It's the impedance, and X is reactance. However, Y, that we call it admittance, is inverse of Z. 1 over Z is equal Y. And the Y is G plus J B is the mathematical definition. So the B is susceptance. So, and susceptance is the shunt magnetizing, that to magnetize the core of the transformer, we use this one. is calculated from the mutual inductance. However, if we want to have more accurate equivalent circuit, we can use this. This symbol is added, and this part is added to the previous equivalent circuit. This one is related to the losses in the iron core. The previous circuit, we neglected the loss in the iron core, but we have two losses in the core. And the first one is related to the variation in the direction of the flux. The second one is because of the circulating current induced in the iron. So anyway, we have two losses in the iron core. And if we want to consider equivalent for the losses, we consider this resistor in the circuit, in the equivalent circuit. And if we want to consider isolation, we can consider ideal transformer in the circuit, in the equivalent circuit that shows we have the isolation here. It's the ideal transformer with losses, with the losses in the wire, with the losses in the core, inductance, and magnetizing parameter. However, it's more accurate circuit for the transformer. Over some time in analysis, it's difficult to use it, and we can make it more simple. And in this way, we can remove this branch and remove this part. And we can, if you remove this, you can add these two parts. So the final will be R1 and X1. That capital R is summation of R1 and A2 R2. Sorry. So square A R2 is this one. If you added these two resistor, we can have R1. And with adding these two inductance, we have X1. It's a simpler circuit, equivalent circuit for transformer. You can use it a lot in the power system analysis. However, in the machine or the special course for the transformer, this equivalent is more accurate, that you can use it. Is there any question from this part? We can go further to voltage regulation. Okay, if not, we can go further with voltage regulation. The voltage regulation is defined with the difference between the voltage magnitude. You have to remember it's the magnitude of the voltage, because it's the voltage we calculate is the phasor, and the phasor is a complex value, and we want to calculate, we want to use the magnitude of the voltage. So we have this formulation for the voltage regulation. We use it a lot in the transformer, and this part is related to the magnitude of load voltage at no load. Suppose that you have no load in the transformer, you want to calculate the voltage. It's the open source. And on the other hand, you have another case, you apply, you connect the voltage, you connect the load on one side of the transformer, and you calculate the voltage, you measure the voltage. The difference between these two voltages is the voltage regulation. but this difference should be divided by the full load as well. So this present is very important in the analysis, but if you use example, you can have a better understanding. But since we don't have enough time, I didn't bring example, but Alireza, next session will work with you about how I use this formula. But just remember, voltage regulation. We use this expression for calculation of the voltage regulation. However, how we can determine the parameter of the transformer? You have reactance, you have resistance in the equivalent circuit of the transformer. You want to know how to calculate this parameter by the tests. So we have two types of tests. One of them is open circuit. So in the open circuit, you have to, here, this terminal will be open. And most of the time, the high voltage will be open, and we apply the voltage source on the low voltage and calculate the power with the wattmeter and the current. According to this test, we can calculate G and the B here. In order to calculate these parameters, you can use this test. However, there is another type of test that we call it short circuit. Low voltage side will be short circuit. And then we calculate the power and the current. And with this test, we can extract R and X here. Addition of R1 and square A R2 and X. So with short circuit test, we can calculate reactance and the resistance. However, with the open source test, we can calculate G and B. This is the parallel branch. It was the test and the per unit. The per unit is another notation that we used in the analysis. Is a mathematical trick that you use to analysis system. Suppose that in the transformer or the synchronous machine or transmission line, you have ohmic value, but these value are different. For example, in the power in the transformer, suppose that you have the impedance here. If you measure the impedance from this part, is different from the impedance measured from this part. So since we have different level of voltage, in order to make the analysis more simple, we can use the per unit. And the per unit means just you have to divide the main value by the base value. So anyway, if you have, for example, Z, the main value, if it is divided by Z the base, so Z will be per unit. This calculation called per unit. However, how we determine the base for the quantities is very important. If you consider the rating voltage in the transformer, if you consider the rating voltage of both sides as a base of voltage, you can have a simpler analysis in the power system with the transformer. So you can say, if you transformer here in the ohmic value, if you convert in the per unit, you will have just impedance in per unit. For example, you had impedance here. and impedance here. It was Z1 and Z2. So modeling of this part is difficult. However, if you use per unit calculation, the transformer convert to a simple impedance that is called, for example, Z3. That's why we use per unit in the calculation. However, you can better understand that how to calculate the per unit of the value with an example. And Alireza will work with you about how to calculate it later. But get familiar with this concept. And the per unit is just a notation used for analysis, and it's dividing to the base of a value. Three-phase transformer. Is there any question? Okay, so we can go further. Three-phase transformer. So till now we had just one-phase transformer, and we had two coil in a one iron core. However, in the current power system, we have three-phase. So we need a three-phase power system, three-phase transformer in the power system. So how to create a three-phase power transformer? In theory, you can add three individual single-phase transformer, and they are connected to create three-phase transformer. You can see you have one single here, another single transform, another one. If you connect them, so you will have for each phase, you will have one transformer. If you connect them correctly, you will have three-phase transformer. However, it needs a more space, and it has positive and negative side. With the three single phase, you need more space, but on the other hand, the reliability of the system will increase, because if there is in the case of failure, you will just lose one phase. But in a three-phase transformer, if something happened for one phase, you will lose whole the system. It's the problem with the three-phase. Anyway, in the three-phase system that is more common, we use this type of core, and you have primary for three phases and the secondary coil for three phases. And is mentioned here as well. And with the three-phase transformer, you require less iron. So you decrease the cost, and it's more economical. So it's a three-phase. However, since we have many terminal in the three-phase, so the how to connect this port, how to connect this terminal are very important. So we have different type of connecting with the three-phase transformer. Based on that, we have 4 types of connection. The first one is called YY. It means that 3 phases are connected in this part is called for example, it's called primary, and you connected in Y form. So you have 3 terminal here and 1 neutral here. And you can do the same for the other parts. If you use the Y connection for both sides of transformer, we call it YY connection. However, we have another type as well. The left side, you use the Y connection, but the right side, you can use delta. That in This form is called delta. You have three transformers are connected in this way. You have three terminals here, but you don't have any neutral line. This form is called delta. So if you have Y for the left side and delta for the right side, we call it Y delta. And if in reverse, you can have delta for the left side and Y for the right side. And the final form will be delta and delta. So both sides we use delta connection. So depends on what type of connection you use. In the three-phase transformer, we have four types of three-phase transformer: YY, Y delta, delta Y, and delta delta. So consider this three-phase transformer. Suppose that here is a load, and here is a three-phase transformer. And we have the source here. It doesn't mention. It's the voltage source, for example. A three-phase transformer is connected to voltage source, and the load is the symmetrical load. We want to know that how to transfer, for example, this impedance, this resistance to another side. We did that with the single phase. In the single phase, you could convert, you could transfer one impedance from one side to another side. We want to know that how we can do it in three-phase transformer. Here is we have YY connection. It depends on which type of connection you use in the transformer. The impedance here is 0.6 that is converted to the other side, the left side, with this ratio. Is 66 is the line voltage, and 6.6 is line to line voltage. Here is line to line voltage of the left side here, and 6.6 is line to line voltage of the right side. With this line to line voltage, we can calculate a ratio of the voltage, and with the square, we will have 60. So it means that from this side, if you measure the impedance, if you measured voltage over current, you will have 0.6. However, if you calculate impedance from here, you will have 60 ohm. So it was for YY connection. However, if we change this type for the connection, this formulation will change. For example, we had this before. We have YY. You remember, you have the impedance here. We want to know what will be impedance from this side. The impedance will be voltage of line to line, voltage of line to line. It's the voltage of line to line this side. It's the voltage of line to line this side. So if you square it and times ZL, the impedance can be transferred to another side. However, if we had delta Y connection, you cannot use this formula for this type. You have to remember this equivalence. If you have an example, if you have a question in the exam that you have a delta Y connection in the three-phase transformer, you have to remember this equivalent. For each phase, you have to consider an ideal transformer, but the turn is different. Here, the turn was N1, N2, but you have to remember, you have to memorize that for the delta Y connection, the turn, the first winding will be N1 over root 3, and the other one is N2. If you remember this one, you can use this formula or this one for transferring ZL to another side. And for Y delta, if you have Y delta connection for three-phase transformer, you have to remember this equivalent, that the part of delta, the turn will not change. It will be N1. But this turn is related to the delta connection, that you have to remember it will be N2 over root 3. And you have to use this expression to transfer Z2 to another side. If you want to calculate ZH, it means that measure Z from this winding, you have to use this equation. And finally, when you have this type, delta delta, you have to remember this equivalent. And this is the turn that is equivalent for the three-phase. And the final expression for the measured impedance from the this side. So therefore, depends of which type of connection you have in the three-phase transformer, you can use different equivalent, single phase equivalent for transformer, and you can calculate which ratio you can use to transfer impedance from one side to another side. It was three-phase and auto transformer. Do you have question? So if not, we can go further. So about auto transformer, you remember that in the ordinary transformer, the two windings are connected with the magnetic field. There isn't any electrical connection. However, if you can create a system that you can connect two windings with both magnetic and electric, you can have auto transformer. Suppose that in the ideal transformer, two windings are not connected electrically. Just some flux is here and they are connected with magnetism. However, in the auto transformer, you can connect them. If you move it up and put it here, you will have auto transformer. So in addition to magnetic connection, we will have electric connection as well. And this system is called auto transformer, and you can increase the efficiency because you have two kind of connection, and you can increase. Suppose that if you have V2 here, V1 here, V2 is summation of this voltage and this voltage. So you can increase the voltage more. So efficiency will be higher compared to ideal transformer. Auto transformer is the last slide for the transformer, and we will go to the synchronous machine. Is there any question related to transformer? Nothing. Okay, so we can go further with the synchronous machine. And the synchronous machine is the AC generator. And you can imagine it's the main part of electrical power system for generating power. And we use a lot in the power system now. Most of them are AC machine. And it is driven by a turbine that convert the mechanical energy to electrical energy. And the synchronous machine has two parts. The first one is stator, that is fixed without any movement, and the rotor. It is rotor that has revolution inside the stator, but the stator is fixed. This one is a stator. And most of the time, a stator is called armature, and it's a stationary part. And it carries the current to the system. So you can see here the currents in this winding that induced, that is sent to the, for example, here is the power system, is sent to the power system. And the rotor is mounted on the shaft and rotate inside the stator. In order to have a better imagination how the synchronous machine works, I want to show you a video here, and I will play it.
Are the workhorse of the power generation industry.
Can you hear the sound?
Yes, thank you. It's clear.
Thank you. So let's go.
It is capable to generate AC power at a specified frequency. It is also called a synchronous generator. Electricity is produced in alternators by electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic field, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary, and rotating magnetic flux associated with the rotor induces electricity in the armature coils. This kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects armature coils, which is fitted around the rotor. This will generate an alternating EMF across the winding. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes 1 complete cycle. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through following relationship. It is clear that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils, which are in 120-degree phase difference with the first, is put into the stator winding. Generally, One end of these three coils are star connected, and three-phase electricity is drawn from the other ends. It is clear from this equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor, and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Or salient pole rotors are used when the prime mover rotates at relatively lower RPM. Pole core is used to effectively transfer magnetic flux, and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to eddy current formation. Armature winding of three-phase 12-pole system is shown here. A stator core is used to enhance magnetic flux transfer. DC current is supplied to rotor via a pair of slip rings. DC current is supplied either from an external source or from a small DC generator which is fitted on the same prime mover. Such alternators are called self-excited. With variation of load, generator terminal output voltage will vary. It is desired to keep the terminal voltage in a specified limit. An automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, AVR increases the field current, thus the field strength. This will result in increase in terminal voltage. If terminal voltage is high, the reverse is done. Hope you had a nice introduction to working of alternators. Thank you.
Okay, I hope it was useful. Okay, so since I need to stop the recording and convert it in my Zoom, I need some time. So please have a break, 15 minutes, and then return back, and we will continue synchronous machine. Is it okay?
Okay.
So 15 minutes. See you.